Hi, everyone. I hope that you're all doing well. In this lecture, I want to show you an alternative perspective on the geometry of regression analysis, which can be very useful. It follows up a video that I made earlier in the series on the correlation coefficient from the same perspective, basically that of linear algebra and in particular, although pretty conventional way of thinking about linear algebra. This video will assume a lot of knowledge covered in that previous lecture, so please go see that if you're interested. It'll be the previous video in this series. So I'm going to start by presuming that you know more or less what I covered in that video. So I wanted to go back and discuss the basics of regression in the kind of typical means of representing regression, which is in variable space. Remember that we defined variable space last time. The variable space looks something like this. I'm going to make a thicker marker this time because I didn't really love the way it showed up last time. So in the traditional way of thinking about regression, we have a scatter plot here, which again is variable space because the variables are on the axes. So they define the space. And we might have a cloud of points that looks something like this. And what we are trying to do is find a line that passes through these points in some way, or on some criteria. So we have basically this setup here that we think characterizes the model at the population level. And our goal is to come up with estimates for beta 1 and beta naught, primarily beta 1. So what's going on here, really? Well, when we have a situation like this and we set that as our task, what we're asserting is that we think, especially if we don't include any other predictors, we really are strongly saying that we believe that y is basically some value of x plus random noise. So someone's score on a particular outcome, say their performance on a particular exam, is just a linear multiplication, or that's kind of, I guess, redundant. It's a scalar multiplication or just a simple scaling of their value on x. So for example, we might have a function that has this specific form. I'm picking specific values just to make this kind of clear. So we might say 3 plus 4x, something like that. And note that this u term here is the error term in the population. And what that basically does is it tells us that here we're saying for some individual, basically, so you can put the subscript in there or not. We're saying that for some individual, they're maybe going to have a deviation from the prediction, the systematic part of the regression here, but that it's random. So it doesn't, tend to go above the line or below the line when we've got, say, higher values of x or lower values of x. So we're not going to be systematically wrong in that respect. And there's some other kind of assumptions too about the spread of these errors around the regression line. But I want to stick to the main point here, which is that we're saying something pretty strong when we do bivariate regression, especially where we say that y is just a linear function of x. What that means is that basically we know, once we know someone's value of x, what their value of y will be, plus basically noise that is, hopefully negligible, right? That's kind of the strong claim here. And when I say negligible, I don't mean that it doesn't exist, but that it's kind of not a major factor in the outcome, basically, that the noise in particular is small relative to the signal provided by this component here. So that's a pretty strong claim, and it's something that's worth kind of meditating on because it points up one of the limits of linear regression. But I'm going to kind of make that point here, not so much to scare you off of regression, although you should be very careful about it, but also to motivate some points further in this video. So the idea here is that we want to somehow get y to simply be some value of x multiplied and then added. And technically, that's known as an affine function. We'll just refer to that as a linear function here. So that's the goal, right? And there's standard techniques using least squares, algebra, or calculus, really, that I can show maybe in a later video. And typically, however, we don't really change this basic picture that we have. But it's very useful, I think, to instead return to our picture from subject space. So let's come down here and let's again draw our vectors. And just as a reminder, in subject space, implicitly there's a coordinate plane in the background here. And the axes, oh, maybe go ahead and draw those in. The axes are given by individuals, which is kind of a strange thing when you really think about it. We'll make this style red here. And I'll give kind of a 3D picture on this. So what this is telling us is that basically there are, n dimensions to our space here, n being the conventional way of denoting the number of people or the number of observations. I recently learned, as I've been reading more of the machine learning literature, that it's actually pretty common in a lot of that literature to write matrices like this. So as m by n, which I find interesting, but also fairly annoying, I have to admit. So I'm using the kind of more traditional means of conventional lettering here. So for us, n by k will refer to the number of rows and the number of columns, which I think is slightly more intuitive since n, most people know, means the sample size in a social scientific context, and k, well, it makes the same sound as c in many cases, and thus it can be held to stand for columns. So that's typically how I'll refer to it, especially because that notation is pretty universal in econometrics, but evidently not in the machine learning community. So this is how we would think about space. It's got n dimensions, and it's hard to picture beyond 3. But the nice thing is we can come up with a pretty good intuition for what's going on here without needing to be able to picture all of those dimensions. And in particular, that's because, as I mentioned last time, this very important fact from linear algebra, that even if you have very, very many dimensions to the entire space, so you say have 1,000 or 2,000, when you only have, say, 2 vectors, so 2 variables, or you only have 3 vectors or 3 variables, at most, those 2 vectors might, say, span a space of 3 dimensions. And in fact, 2 vectors span a space of only 2 dimensions. And in particular, when you're thinking about basically 2 separate spaces, as we will in this video, it turns out that even though you can see here, I've drawn this vector x as being in 3 dimensions, it's actually in one sense only 1-dimensional. So this is kind of an important point, and it actually has to do with the point I was making before about the process inherent in regression, which is that we're basically trying to do some kind of information reduction. So regression is a phenomenon whereby we're trying to reduce the complexity of something, which can be both good and bad, right? Even just when I say it like that, you're probably thinking about some nice things, like being able to better understand a complex idea, and some not so nice things, maybe taking a complicated social situation and reducing it to something that is maybe oversimplified. So that's the basic principle behind regression. So note here that this single vector x spans a 1-dimensional space. And what does that mean, to span a space? Well, formally speaking, what it means is that a vector, or commonly a set of vectors, can hit every point, or in other words, some linear combination of the vectors can result in every vector in some space, right? And so that kind of gives us a sense for what's meant by space in linear algebra. So for example, if you think about the real number line, right? The real number line is a space that is one-dimensional. And if we think about writing out here, the number line, and let's say this is 0, and this is 3, and maybe we're going to go out to, let's say, here some value 7, or let's actually make it 9 for simplicity. So what this means when we say that this vector 3 spans this space is that we can multiply 3 by some constant here. That's implicitly, of course, 3 again to get to 9. But we could pick any old number. So in that sense, the vector 3, which is just a number, but you can think about it as a special kind of vector, spans the real number line, meaning that multiplying it by some value gets us to anywhere in that real number line. So then the idea is, okay, well, what happens if we have one vector, which is in some senses like just one number and in some senses not? So let's say we have the vector, let's pick a simple example that's different to our problem. Let's say we have the vector, how about 1, 1? We'll call this vector v. So how many dimensions does this span? Well, what you might realize is that even though this is a vector in two-dimensional space, it really can't go anywhere because it's still just one vector, much like our single number was just one number. So if we think about extending it out here to say something like, we'll call this alpha times v, let's say this is, well, let's not even give it a specific number. We'll just say this is alpha times v1 times v2. Maybe alpha is equal to 3 or something like that. At most, what we can do is multiply by positive and negative constants here, and we could go in the opposite direction. So this maybe is negative alpha times v, which is equal to this here. And that's not exactly drawn to scale, but you get the picture. So the idea is that we're actually not spanning a space that is, in any sense, multi-dimensional. Yes, there are two coordinates here. So there's the what you might want to think about as the x-coordinate and the y-coordinate here and here. I don't think that's very helpful, though, because the point is, well, there's a lot of reasons that's maybe not as useful. So you can just think about it as the first and the second dimension, which happen to be the two dimensions of a plane. So we do have this multi-dimensional thing. We have this vector, right? But the point is that it can't leave the line that it's on. So in other words, it doesn't actually span a plane. We can't describe items in the rest of the plane, like we can't get to, for example, some point up here, or some point over here, or some point over here. We would need a second vector, which we can just write in here. And we'll just call that, I don't know, the vector q. And notice that we could take q and stretch it. I'll show you what that would look like. We'll copy it here. We could take q and stretch it. And this is actually a little bit tricky with this orientation. So maybe we need to come down here and, okay, this looks good. Something like this. And we could say stretch q. Sorry, I forgot what I was doing here. To reach this point, once we've transformed v and we've multiplied v by this amount here. I know that's kind of off the line, but that might actually be helpful for visualization. So we can say that we can reach this point here. Let's call it P. So this point P here, which is actually also able to be described as a vector, is equal to a linear combination of the vector Q. We'll call this alpha times, actually, let's call it something different for simplicity. So we'll call this beta times q plus, and we'll call this one here just, I don't know, gamma times b. And we can put this into matrix form, of course, by just saying here we've got this set of what are called basis vectors, q here, v here, so these form a matrix. And then we can just put these guys in a vector here, and we could give the vector a separate name. But note that what happens when you do this matrix multiplication is this becomes what we just saw before. So that's the linear combination perspective on matrix multiplication. So the point here is that we would need to add in a second vector to actually span the plane. We can't fundamentally move off of this one line. So we can't actually travel in multiple dimensions in a sense. Even though the vector itself is in one dimension, we can't move off of it. So we can only move along one axis, basically. And that's what it means for that vector to span only a one-dimensional space. And all of this is actually pretty important. So what's our goal next? And let me go ahead and copy this down. What's our goal here? So now to reframe our goal from what it was before, our goal before was to find some constant that we could multiply our x's by. Whoops, that was not good. Oh, can't seem to get that little bit to leave. Oh, it's how did I accidentally? Sorry, folks. I somehow copied this, I think, as an image. That's pretty annoying. Yeah. There we go. So our goal was to find some value that we would multiply all of the x's by, and then that would ideally match up with the value of all of the y's, respectively. So we could multiply every individual's x by some constant, and we would get every individual's y, respectively. Now, that's not possible, of course, because if we look at it, these points up here obviously don't all lie along a line. The idea is that if this is a well-modeled function, so it really is the case that y is just a function of x and nothing else, that could be true, and it could be the case that x is still a bad model for y. But the idea is that, hopefully speaking, hopefully if we're doing regression for the right reasons, x should be a pretty good predictor of y. We shouldn't have a lot of kind of random noise left over. There's maybe a strange case where it could be that x is the best predictor of y, and y is still just hard to predict. Pardon me. The idea is, ideally, the relationship should be fairly tight, right? If we're asserting that that's our model. Okay, so that was what our goal was in variable space. So how does that change here? Well, the idea is that we now want to put our vector y, our outcome, in the space of our vector x. So what that means is, because now people's scores are represented as coordinates of this vector x, what we want to do is the same thing as before. We want to multiply every coordinate of x, or in other words, every person's score on x, and then hopefully get y out of it. And again, it's not going to be the case that we can do that exactly, right? For the same reason that we saw before, except the geometry of it's a little bit different. Before, we saw that the points didn't all actually cluster along a line, right? As soon as there's 3 points and 2 of them are on a line and the other isn't one, we, by definition, then don't have a perfect match between the two. But the idea is that, hopefully they should be sort of close. So we have the same problem here, right? We've got 2 vectors here, and they lie in different spaces, right? So we've got this vector here, right? This vector is in n-dimensional space. And here we'll just say it's a actual, in the number of dimensions that we're in, you can just kind of generalize those. So y is a member of three-dimensional space, and so is x. But note that they each span a space that is not actually the same space. We can't, it's visually obvious. I don't need to assign any kind of dummy values to x or y to show you that by just multiplying x by scalars and multiplying y by scalars, I can't somehow get one of them to be where the other is. So the idea then is that we have this kind of next best step in linear algebra, which is an operation known as projection. So the idea here is, what if we somehow get y down into the space of x? And then what we could do is say, well, of course, then at that point, we can multiply x by a scalar. And scalar, by the way, just means a single number as opposed to any kind of vector. And then we could multiply x by it and get that projection, as it's known. So here's a way to think about this problem. We want x to be as close as possible to y here. In other words, we want our multiplication of x to get us the closest we can to y, even though we can't actually reach y. And this is analogous to the process in the variable space picture of trying to find a value of x such that the line minimizes the sum of squared distances from the line. So you could think about a couple of candidates here. Here's one. Here's another. And here's another. Now, which of these is best? And there's many others. No, you could have one here. Which of these is best? So you may be unsurprised to learn that we're going to consider this one best, right? So why is that? Well, it's because this is the shortest distance, right? Hopefully that's intuitive. There are proofs out there on the internet if not. But the idea is that if we just directly project this outcome y right down onto the space of x, note that we're only traveling in one direction here. We're not traveling simultaneously in two different directions as we are with these cases here, here, and here. So if you think about it, maybe the simplest way to put it is just that the shortest distance between any 2 points is just a straight line, right? And so that's the case where we're going exactly straight, and that's going to minimize the distance. So that's the idea. And then we'll get to the formula soon enough because the formula is actually quite pretty. But what we're going to do here first is kind of express what this would look like. So what does regression look like in this case? Oops. Let's choose blue here. So this is what we want. We want to find the coefficient and we'll just denote this beta 1 actually, such that the distance between x and y and will actually now, sorry, it's not really x, but let's denote by our best guess at y in the space of x. Let's denote that now with the kind of familiar notation of y hat, so that the distance between y hat and y is minimized. Just like we think about it normally in variable space, and like you might have learned with some basic methods in multivariable calculus, which are typically taught as means of deriving the ordinary least squares regression estimators. So that's our task. So what this is here is this vector here is actually our estimated coefficient beta hat 1 times x, i.e. y hat. So that's our task. We want to come up with that. Now, there's a couple of ways of thinking about this. And so you might want to stop and think, how could we come up with that? But I would say there's a pretty intuitive way to think about this. So let me lay this out now. So the first point is that in linear algebra, when we want to express the perpendicularity of two vectors, and note that these are perpendicular, there's a condition known as orthogonality. And orthogonality is a pretty deep concept, but I'll just share with you a really intuitive way of thinking about it. If two vectors are orthogonal, their dot product is 0. So if v1 and v2 are orthogonal, v1 dotted with v2, which is also the same thing, note as v1 transpose v2 is equal to 0. So this is an important property. And there's a really nice interpretation here. So let's assume for the moment that we have centered vectors as we did before. So assume centered vectors. Right? So then, again, what would it mean to have the dot product? So that property is this. We can actually interpret this dot product here as basically being, as we actually saw in the last video, the numerator of the covariance. And since the covariance just scales the dot product and the correlation coefficient just scales the covariance, we can basically say that when two vectors have a dot product that is equal to 0, that in most cases is going to mean that they basically just have 0 correlation. There's some technicality it's not worth going into here. So note that we can actually write this in a kind of clever way. So first I want to show you that the residual vector, and we're going to write that as E, even though that could easily be confused with the error term, which is the true unobserved population level difference between basically the prediction and the outcome. So prediction has two meanings in classic, kind of linear regression. One, you have sample data and you're making inference about the population. Two, it's just generally the case that one variable we don't think generally perfectly predicts another, even if we knew the population. All of that is to say that it could be somewhat confusing to use E, but that's all right. So what is that residual vector going to be? And I don't use R because it's liable to be confused with the Pearson correlation coefficient. And also at the same time, many authors use E. So what is this equal to? Well, by definition, this is just equal to the actual predictions, or actual values, pardon me, minus the predictions. So this y hat here. And you'll sometimes see people write this in a reverse way as well. And that is generally context dependent, usually in classical statistical or applied statistical settings. It's just taken for granted that this is how the residual vector is written. In machine learning contexts and general situations where you hear people talk about objective functions and loss functions and this sort of thing, you might see people actually define it differently. And a lot of the quantities that we're going to use in this video, like the meaning of X, for instance, in those settings, usually is in the classic linear algebra sense meant as the vector of variables, but for X, X will be a matrix of data. So anyways, just a word to the wise. So what is this equal to? Well, here, this guy is going to be mean-centered because we centered the variables, and we'll come back to uncentered regression later. And then this guy is here equal to whatever our estimate ends up being times mean-centered variable. So that means that the sum of these residuals, right, and we can just actually go ahead. We could write this, we could write the sum in vector notation, but we don't need to. So we'll just write it like this. So the sum of these residuals then is basically, let's rewrite it like this. So equals sum of the actual observations, slightly tedious, but I will write the indices here. And to make it just simple, let's write this as plus negative, and then so this sums to 0. And so does this. So that means that the residuals in the case of mean-centered variables are going to be mean and sum 0. And it follows, by the way, hopefully, obviously, the sum is the important part. So since the sum is 0, the mean also has to be 0. That's a basic law of arithmetic. The other important point here is that we didn't include an intercept in this regression. So in the centered context, when you would include something like a vector of ones in your data, that has no real meaning here because the mean of 1 is 1. So centering that vector of constants that you add would just end up in nothing. But we still have the same classic situation as we do when we have uncentered regression, which you're probably more familiar with. We still have a residual vector that sums to 0. Okay, so what does that mean? Why did I bother pointing that out? Well, what this means here is that then if we write dot product of our variable and our residuals, and we say that that has to be equal to 0, and we can be pedantic and write that as a 0 vector. Oh, wait, sorry, we actually don't need to do that because it's going to be a scalar. Phi on me. So let's go ahead then and write out what this actually is. So technically speaking, we can rewrite the dot product like this, right? This is just, again, the definition of a dot product. But note that technically speaking, we can say that we're taking the mean of the residuals and then the mean of x bar. Remember, this is a centered variable, right? So we can either think about that in one of two ways, but probably the simpler way is to just think, yeah, technically here the mean is 0, so we're writing it out like this. Now notice that this is the numerator of the covariance, and depending on how you express the correlation, also in many expressions is the numerator. And we're saying that this has to be equal to 0. And then what that means then is that for all intents and purposes, this means that the correlation coefficient and, whoops, we should use the correct mathematical notation here, and for good measure, the covariance of the two is equal to 0. So intuitively, that orthogonality condition basically comes to the same thing as saying 0 correlation between the residual and the predictor. Okay, so now let's put that into some practice. So we need first to rewrite this in a clever way. So here I'm just swapping the order, that doesn't matter with dot products. But let's write out what that residual is. And we already wrote this out once before to make the point. So it's by definition going to be whatever we decide on for, and why don't I actually write this with a tilde here since we haven't yet figured out what the beta is. So this is equal to basically the actual outcome. And by the way, that doesn't mean matrix here. Underlining can be confusing in linear algebra. So the actual outcome minus the regression slope times the variable itself. Okay. So we can go ahead and distribute this dot product. For more on why that's possible, you can see my previous video. Although just as a reminder, since it is kind of an important property, here's a way to think about that. So if we write out, again, the dot product, let's just do something simple here. And we'll say like x dotted with, let's just say something like y plus z here. And this is just an example of why that works. And we need to put some subscripts here and then get rid of the vector notation. Sorry about that. So that's basically what this is saying if we take the dot of those things. And then if you really think about this, now you can just distribute and then do the addition in the end. So this is equal to right. And then if we go ahead and try to turn this into a dot product, this is simply the dot of x and y plus the dot of x and z. So we can distribute. And let's go ahead and do that. Okay, now we can do a little bit of rearrangement. This part's pretty simple. Hopefully you can follow along here. If not, you probably want to review some of your fundamental algebra and then come back to this material later on. So that's a terrible Y, but you get the point. It's actually so sloppy that it might be distracting. Let's fix. And then finally, and we can replace this with a hat because we're now at the final stage. So the actual predicted beta is this. Now this is very exciting because you'll notice something cool. We remember that these are centered. If centered, what this becomes is and remember that when you have a dot product of something with itself, that's the same thing as taking the sum of squares of the thing, which is also, as we saw in the last video, that's why the dot product is also intimately connected to the length. So the dot product of a centered vector is equal to the squared length of the vector, and it's also equal to the kind of sum of squares associated with the variable version of the vector. So that's a really powerful notion. So if this is centered, we get this, and notice that this is just immediately equal to the regression slope formula in one way that you may have learned it. Now you may have learned another way, which is this. So equals R times, probably shouldn't write the dot there since we're discussing dot products, this, right? But what is this equal to? This is equal to covariance of x and y over standard deviation of x times the standard deviation of y times this. So these cancel, and this is equal to the covariance of x and y over the variance of x, because note that the standard deviation of something squared is the variance. Okay, so that's a very cool property. And that gives us a really nice way to justify the reason that the regression slope in two variables is what it is. So there's a number of cool facts that follow from this. I'm almost so excited to share, I don't know where to begin. I think maybe the most interesting one to start with is now, how do we do our regular regression diagnostics? Well, let's go back up to our picture. I want to copy that down here. So I've got some scratch work down here from another video. So let's go back here and think about how we could conceive of our typical regression diagnostics. Well, you might know that two ways of assessing fit are one in bivariate setting, literally r squared, and to make that obvious, write the two variables on which it's a correlation, or model sum squares over total sum squares. And note that the notation around the latter pair of terms is possibly the worst case of notation hell that I've ever seen in my life. It's really terrible. So you'll see things like people writing the sum of squared errors, which is wrong. It's the sum of squared residuals. Then you have the even worse phenomenon that some people write sum of squares explained to mean the model sum of squares, which then, it's really just a complete mess of a situation. So my terminology is model sum of squares, total sum of squares, and residual sum of squares, which is pretty much how Stata, the statistical software that I use most, although I use R and Python also, uses them, although Stata power users will know that Stata unfortunately refers to the root mean squared error rather than residual, but otherwise Stata is pretty good. But yeah, there's a lot of older textbooks that use just absolutely horrendous notation on this, and it confuses people very badly. So anyways, these are our two traditional diagnostic measures, right? So how can we think about that here? Well, let's look at the second one first. So note that the model sum of squares is defined like this. And then the, oh, pardon me, sorry. So note that the model sum of squares is defined like this. And the total sum of squares is defined, of course, just as the numerator of the variance. So how can we make some sense of that in terms of our picture? So here's the idea. What we're doing is we're actually taking our outcome vector and partitioning it. So note that there's this really interesting fact. So let's actually look at the geometry here a little bit more. Let's come back to this. Pick a new color. We'll pick a nice lime green here. So this is basically a triangle. And we've seen before that vectors, in many ways, make a lot more sense when you start thinking about them as the hypotenuse of triangles and arbitrary numbers of dimensions. And this is indeed the case here. So what that means is that we can say, generally, the hypotenuse squared is equal to leg 1 squared plus leg 2 squared. So here the hypotenuse is what? Well, it's the outcome vector. And remember, our vectors are squared, or centered, pardon me. So what we're going to say here is that the squared length, which is just the total sum of squares here, is equal to leg 1, which is going to be this. So it's y hat I. And then note that our outcome vector and because our outcome vector is just a scaled version, sorry, our prediction vector is just a scaled version of x, that means it's also got mean 0. So this is technically also right here. This vector right here, this prediction vector, is also a sum of squares about the mean because technically the mean here is also 0. So, and then finally, plus our residual vector. Oh, sorry, making silly mistakes all over the place here. And so that's equal to the total sum of squares. The total sum of squares is equal to the model sum of squares plus the residual sum of squares. So that's a really cool fact. But here's another neat way to think about it. So let's divide both sides by the total sum of squares. So we get 1 is equal to model sum of squares, so the total sum of squares plus the residual sum of squares minus the total sum of squares. So what this tells us then is that if we take one as kind of representing the total, or one as being a stand-in here for what some people might be more comfortable thinking of as 100%, we could actually scale this by 100 too if we want, and it would have the same meaning, but we don't need to do that. What this is telling us is that the model sum of squares and the residual sum of squares, when taken as fractions of the total sum of squares, have to, like, they have this obvious fact that they have to sum together to one. So we can actually think about the regression procedure as partitioning the outcome vector into an explained portion and an unexplained portion. And when the explained portion here is high, that means that we have a good fit. And when the explained portion here is high, we have poor fit. But notice that what that also is telling us is that it's giving us the ratio of the squared length of this thing to the squared length of this thing. So in other words, when these two lengths are big, meaning that we can, or sorry, when the ratio is big, that means that the prediction vector is close to the length of the outcome vector. But when they're small, so when they have little shared relationship, so let me just draw a picture in two-dimensional space of what that might look like. So here they're almost orthogonal. If we project that down to here, and by the way, these residual vectors are technically also from the origin here, but it's just convenient to draw them at the tip of the outcome vector. So in this case, notice that this ratio here, so MSS here and TSS here, so MSS over TSS here is small, whatever that exactly means. So that's an example where the vectors are angularly distant, and simultaneously, that also means that the share of explained variance is small. Now, you may be wondering, why bother with these squared lengths, right? And so that's actually a really interesting story. So let me just show it to you in terms of a little bit of high school geometry. So remember that the equation that this is all built around is simply the Pythagorean theorem, which is turns out to be one of the deepest theorems in mathematics. So notice that what we're basically doing here is dividing both sides by c squared and kind of screwed that up there. Okay, so what we're doing is this, right? Silly as that looks. When we do our equation above, where we kind of show that these two things come together. But note that the following is not true. So let's say we take the root of both sides, right? Okay, so that means that I won't be tedious and show all the steps, but c is equal to root of a squared plus b squared. Note that a squared plus b squared taken to the power of 1/2 or rooted is not equal to this. Right? Because if we think about it, so what is the right-hand side? Well, that just equals a plus b. And this here is obviously not going to be a plus b. Hopefully you can see why. One way is we could just expand it, right? So why don't we try to square both sides? And then what we get back, this becomes this here. So this is not equal to a squared plus 2ab plus b squared, meaning that the actual lengths don't have to stand in a nice intuitive relation in the same way that the squared lengths do. Their relationship is more complicated. Okay, so let's also think about a cool fact. Let's come back up here one more time just to get our visual perspective and keep copying down this picture. So here's the second way of assessing fit. So if we think about it, in this part, hopefully this kind of review, you probably remember that it is the case here that this is equal to this. And that's true generally. Whoops, sorry, I hit my iPad there. That's true generally if you think about r squared as referring to the prediction vector rather than the simple correlation coefficient. But I want to show you basically what's happening here. So here's this really interesting fact. Note that if you look at this figure here, we have a right triangle. And so before, remember that by definition, well, not by definition, but we found that the angle theta here, found that the cosine of theta is equal to r xy. That was a payoff from the law of cosines. Now note here that because this is the right triangle, we actually don't need the law of cosines here. So when triangle is right, cos theta, of course, is just equal to, anyone, a little bit of high school geometry, adjacent over hypotenuse. So what's the adjacent here? Well, the adjacent is the model sum of squares. We just went over that. And then the hypotenuse is the total sum of squares. Meaning that, or sorry, they're the roots of those things. Right? Because those are the lengths. So meaning that if we square this here, then we have our same equation. So what that means, and by the way, this also here equals, remember, this, because of this. And remember that in this notation, which is potentially confusing, this means the cosine of theta squared, not the cosine of, that's confusing. This means theta's cosine squared, not theta squared, the cosine of. So that's the reason that those two things are equivalent, which is also a really nice fact, even though it doesn't generalize beyond this point, because then we have to start thinking about the prediction vector. Here's another way to thinking about this, even just one more way. If you really think about it, the cosine of theta can't change when the angle is fixed. It's just that before, when the two vectors didn't form a right triangle, we didn't have an easy way to calculate it. That's actually one way to think about what regression does, is it takes these two vectors and it scales the regressor vector so that it forms a right triangle with the outcome vector. So that's a really cool thought, I think. Okay, so the next point I want to show, the next cool thing, and this will probably have to be where this video ends more or less, is that we can also extend this to the case where we've got a constant included. I guess probably I'll also show the general formula for the OLS regression estimates. So if we include a constant, you probably are wondering about that, right? Because in most cases, even though it's a good idea to center vectors, I'll just share one brief reason. So why center vectors generally? Here's an example that I like to use. It's not the best idea to always center them, but here's just one case. Let's say we have an outcome that is earnings. And let's say we want to model earnings as a function of age, job tenure, plus their interaction, plus some beta naught, plus some unobserved term. Okay, so what does this tell us really? Well, if we are trying to interpret the coefficient on age or tenure, note that age and tenure both show up here in two places. So age, the coefficient of age, so beta 1 is the coefficient on age only if tenure equals 0, because otherwise we'll say unit increase in age leads to beta 1 times 1 plus beta 3 times 1 times tenure. And that's a little bit hard to interpret, right? Especially because it's not super plausible that tenure would be 0. Certainly it's not plausible that age would be 0. And so then we have a difficult sort of interpretation. It's not difficult, it's just sort of silly and unrealistic. So if you have centered vectors, then this is how this works. We would say that in many ways, this is actually a nicer interpretation. Oops. And then we can just say that this is the deviation from mean age times beta 1 plus so what this does is it means that if we want to just interpret the coefficient on beta 1, it's more realistic, because now what we can say is coefficient on beta 1 now means effective a 1 unit increase from mean age when tenure is average. So that's a nice reason to generally center vectors, at least in a lot of contexts. So I think I'm stealing that example outright from Jeff Wooldridge, but it's kind of a cool one. So now let's think about what would happen, though, if we did have uncentered vectors. So here's the first point. When you center a vector, we'll point this out here. You center a vector, you partition it into two orthogonal spaces. So here's an example. We'll just write it out very abstractly first. So we'll say that let capital Y equal this vector of means plus this little vector of deviations. And this notation comes from Tom Wicken's excellent book, which I would say these lectures are 80 to 90% based on. I've incorporated some other things, principally from the work of Vandenberg and Boyd, but some other people as well. Wooldridge and Davidson and McCann would also be in there, by the way. So basically, this is the idea, right? Is we can decompose any old vector into these two subspaces. So just a vector of the means and a vector of the deviations. I'll write this in here. Okay. So here's an example. So Y transpose is equal to this row vector 2, 4, 6. And then we can say 2, 4, 6 equals, so hopefully you can immediately see that the mean is 4. Plus negative 2, 0, 2. Right? And you can check the math for yourself there. So that's true. Now notice also that the dot of those two things, little y there, it's not really that clear that it's a y, but if we dot this here, what do we get? Well, we're just going to get -8 plus 0 plus 8 equals 0. So in other words, the vector of deviations about a mean and the vector of the mean is just equal to 0, which is a pretty cool fact in a way, right? And so how can we justify that? So how can we use that fact? Well, what that tells us is that the sum of the deviations is equal to 0, just the principal fact about it. So then what we have here is we can basically say that the mean vector y bar is just equal to y bar, the scalar, times a vector of ones. And then this is dotted with the deviations. And so we can do a nice little bit of just algebraic rearrangement here to make this as obvious as possible. And then what that equals is y bar times 1, well, yeah, 1 times div1. I guess I'll be a little bit pedantic here, plus 1 times div2 plus 1 times div. And in other words, this is equal to so this is equal to 0. So that means that the vector that consists of the constant, whether the mean is, the vector that consists of the mean, whether it's 1 or whether it's the mean itself, that these are orthogonal spaces. And the reason for that, by the way, is the vector of constants is just the vector 1 multiplied by some scalar, as I showed it here. So that means that the deviations and the constant are in orthogonal subspaces. And a fact about orthogonal regressors is that when you do multiple regression onto truly orthogonal regressors, there's no difference between just doing a pair of separate regressions. So that's a fact that becomes very useful later on in multiple regression. But for now, what that means is that we can actually just treat these two subspaces as being totally separate. So how could we put that to practice? Well, let's go back to our outcome here. And we'll again write big Y is equal to beta naught plus beta 1 times big X, and then plus some vector of residuals here. Right, that's going to be our model. But then what we're going to do is bust that up into two things. We have our mean vector plus our little deviations vector. And then we have, let's go ahead and write that 1 in here. So beta naught times our vector of 1s plus beta 1 times this here, our big mean vector plus our little deviations vector. And then if we go ahead and figure out, well, these actually come into two orthogonal subspaces. So what that means is we can treat this in two parts. And we'll say here, we can do a little bit of clever arithmetic again. We'll say beta naught times the 1 vector plus, now this part, beta 1 times x bar here. Notice that this reduces to following. So what this is telling us fundamentally is that these are just scalar multiples of one another. And a really, nice way to put that is that these lie fundamentally on the same line. So if we come down here and we just draw our 1, 1 vector in here, that means that something like this could be our right-hand side. So these lie on the same line, and all we need to do is just figure out how to scale them so that they equal the same thing. And I should draw our y bar in here. So these are all on the same line. So how do we do that? Well, now the easy part, we can just ignore the vector of ones, although you don't have to. This is just one way to think about it. And then what we want to do is just solve the simple one-dimensional algebraic problem here. And this leads to our famous formula for the regression intercept in the bivariate setting. Now, what that means, again, is because the outcome, and this will be a little bit artificial in 2 dimensions here. I'm just drawing it in 2 dimensions for convenience. Don't think too hard about it. Imagine this in more dimensions. What that means is that all the action here is going to happen in this subspace over here, and or in a pair of subspaces. Again, you could maybe think about it in 3 dimensions. So like, let's say here, maybe this is 3-dimensional, and you'll have to imagine that there's like 2, these are kind of like rotated around. So these 2 spaces here of the deviations, this might be little y, and this might be little x. These are both orthogonal to the 1 vector, even though they don't have to be orthogonal to one another. And actually, if they were, that would be a big problem for regression because it wouldn't work. Or it would just produce nothing. But you can see then we do the problem in a separate regression space. So that's the idea, and the rest of the problem really doesn't change anything. Finally, let's do as promised and extend this formula to the general multivariate case. And that'll also tell us, by the way, why it is the case that we have a situation where the sum of the residuals and thus the mean is still 0, even though the variables aren't centered. So how could we express our same idea as before, that we want this orthogonality of, say, like 2 different predictors to the residuals? So that's kind of an interesting question, and we want to think about how to write that. So we want to say here, we want the entire vector of x's to end up being orthogonal matrix of x is to be orthogonal to the residual vector. So let's think about a way to write that. So first, what if we want the residuals to be orthogonal to a vector of ones, since that, the ones are constant, they're the predictor. So many people don't necessarily realize that, but when you include a constant in regression, which is automatic in Stata, R, Python, and so on, what that means is that you're temporarily adding a vector of ones to the data set underneath the hood. Let's actually come back to that problem, though, because I think that actually almost spoils the fun. So let's assume we had multiple predictors. So let's say we've got 2 x's. So how could we write that conveniently so that it's obvious, and we'll write it in the shortest way possible, that the residual vector should be orthogonal to both of them? Well, I kind of like this idea. So what if I said, well, I want basically this to happen, and I want this to happen. And then I might remember that there's now, this is one of the times where it's actually quite convenient to think about matrix multiplication, not in the linear combination sense, but in the sense that if I've got this set up here, where this vector here is k by n, and then this vector here is n by 1. But I take basically some vector here, I flip it on its side, and then I basically then take the dot product with the vector here. So what that means then is that if I write out the matrix multiplication or the dot product in this way, like this, that means that this can just be interpreted as the first row of a matrix that I want, right? So we can just say, I want a matrix filled with, and let's just say we have the 3 predictors. So x1, I'll just write it as a vector of vectors here. So x1, these should have vectors, by the way. Transpose, x2 transpose, and then 1 transpose. And then if we agree that these comprise the data matrix, then this is just x transpose times, whoops, I'm writing the other notation for residuals, times the residual vector. And then again, what that equals is this. So and then what that equals is this. And then we want that to be equal to 0. And then our next step is this. Doing a little bit of rearrangement here. Oh, and this, sorry, should not be transpose. And then what that gives us, now we can't divide using matrices, but we can multiply by inverses. So we have this. As in the famous formula. And we can do a quick kind of spot check here. So the dimensions are a nice way to check. So here, this is what? So this is a k by n matrix multiplied by n by k matrix, which is a k by k matrix. Then here is a k by n matrix multiplied by n by 1 matrix, or a vector. And then that means here that we've got a k by 1, a k by n, and then dimensions of that will all be k by 1, which is standard because beta, the vector is a vector of k column here of k coefficients for k predictors x1, x2, xk. So that all checks out, which is really nice. Oh, and I just noticed I made a little mistake here. Should be out like this. So one last thought here. How does this show that the residual vector will have a sum and thus a mean of 0? So here's how you can check that. Recall that one of the x's is the one vector. And then what that means is that one orthogonality condition is that like this equals 0. And that means that the sum of residuals and thus the mean is 0. So that's a consequence of including that vector of ones in the data matrix. It means that the residuals ultimately also have to be orthogonal to that space, which means that they sum to 0 as well. And then again, note that because we can, generally speaking, think of regression, even if we don't center the variables first, as happening in two orthogonal spaces, that means that the centered regression space is fundamentally basically the correct way to think about regression, whether or not you actually center your vectors, because that's sort of happening under the hood anyways. So thanks everyone for watching. This has been a fun video to show. In future videos, I will talk a little bit about multiple regression and the Frisch-Schwa level theorem. And then I'll also talk a little bit about the calculus proof, the least squares proof for this equation as well. So stick around. Thanks for watching.